Hi, I'm Brian Iverson. I'm the CEO of US Engineered Wood, and I'm the inventor of the T-Stud products. Okay, so I'm going to run you through a little story, but I'm going to first start out with this. I've been asked recently how to best explain a return on investment. So if somebody buys a T-Stud, how do they justify the cost of the T-Stud, and do they get a return on investment? And I got to thinking about that. So the energy codes that are coming up, which I have right here, the energy codes that are coming up, so I'm going to reverse the question to you. Has the state that's going to enact the new energy codes, have they told you what your return on investment is going to be if you spend $2, $3, $4, $5, $10,000 at increasing the R value of your wall assembly or your overall assembly? Have they told you what you're going to get for a return on investment? Has the city told you what you're going to get for a return on investment? Have they told you if you make the wall this much more energy efficient, and if you do this and if you do that, are you going to be able to reduce your furnace size, right? Because if you make it more energy efficient, you would think, hypothetically, that you'd be able to reduce your furnace size, and you'd be able to see the savings in your heating and cooling bill, your HVAC costs. Okay, so I don't know if they have or not. I actually don't think so. And so I asked Mark Willey today, why hasn't that ever come out? Why hasn't anybody ever brought up what the return on investment is of anything, no matter what you do? Why don't they do that? He goes that it's because of liability. He said, I think it's because of liability, because not everybody builds the same way. Not every builder builds the same way. And so that was interesting to me. And so I'm going to run you through a few things, because I have case studies here, and I have a lot of them when it comes right down to it that says that if you build to this standard, this is what you should be able to expect, okay? And this is a straw, okay? So we're going to talk about the straw today, because I live in Minnesota. We created in the state the most energy efficient laws in the 80s and 90s, and we made houses too tight. And they didn't allow or plan for HVAC costs if you make your structure so tight. And if you end up with a little pinhole through the wall, what happens? So anyway, so I'm going to bring this up in a bit. Okay, so here's your energy code. So climate zones 1 through 7. This section right here this is the United States. This is Canada over here. And 2015 is for the most part what's been adopted in the United States, and in Canada 2017. There are more energy codes coming on the East Coast, West Coast, Canada, Alberta, British Columbia. They're all coming. Nova Scotia is probably the most advanced. So what I'm going to tell you is that climate zones 1 and 2, that would be Arizona, Florida, in the farther south, warm climates. You have to meet an R value. They tell you what you have to have in the cavity. So the cavity, and you have your studs. They're going to assume that you're going to have heat loss and heat gain through the stud itself. They just know that that's going to happen, because nobody, when they created these codes, they never knew that the T-stud existed. Okay, so they're assuming they got a stud, and they only tell you what you have to put into the cavity. You have to put an R13 in the cavity. Funny to me that the energy code down south isn't more strict than what it is in the north, because air conditioning costs are 3 times the cost of heating with natural gas, because your electric costs are 3 times as much per BTU. Okay, that's a whole nother story. We're not going to go into weeds on that. Okay, so climate zones 3, 4, 5, 6, and 7. They're telling you that you have to have cavity insulation in 3, 4, and 5, you have to have a cavity insulation of R20, or if you still build with a 2x4 wall, you can do an R13, but you got to put an R5 of foam on the outside of your stud, okay? So if you do one or the other, that's what you have to do, and you meet the energy code automatically. In climate zone 6 and 7, you have to have an R20 and with a R5 on the outside, or you can have an R13 and then do 2 inches of foam on the outside. So, okay, that's all well and fine, really simple. I can go do that, off you go. There's also an alternative method. So if somebody is smart enough to be able to calculate the whole wall of an assembly, so 12 feet by 9, let's say, of how you want to build, you can do what's known as a prescriptive path or a performance path in order to make that same code. And then you have to know how to calculate the U value, which this is seriously in the weeds, folks. So 1 divided by the average R value gives you your U value. So they say, meet the U value. If you know how to do this, off you go. So we meet every energy code in the country with the bare naked T-stud, the simplest way to get a thermal break through the wall. Every single wall assembly we beat, 1 through 7, and all you do is put in blown-in cellulose, and you beat the whole energy code, and you never had to put foam on the outside. So we're the cheapest way to get to meeting every energy code out there without having to do foam. But if you did use foam, that's all the more energy efficient the wall will end up being. So we meet them all, okay? So that's that. If you ever want this info, just send us an email to info@tstud.com, and we'll send you all my propaganda. Okay, we're sending you this as well. So this is the 5.5 inch, the 7.25 inch bare naked. And so we give you the average R value, and the U value, and we give you the Canadian metrics, plus you get a thermal break through them all. Okay, so this is a perfect recipe. We're going to talk about this recipe in a second. So we make and meet every single energy code in all of North America, and most of these beat even the 2021 energy code that they're talking about. Okay, so we're good. We're the number one solution that's out there, dollar for dollar, pound for pound, however the rest of that goes. I know that this isn't clear. Okay, sorry, it's not your eyes. So this is a document created by the National Home Builders Association and the Energy Department in the United States. So they have tracked houses built before 1950 to 1959, all the way up to 2000 to 2009. And so they track how much energy use has been used for HVAC costs, and then they quantified it all the way backwards to anything built between 2000 and 2009. You use 34,100 BTUs per square foot for HVAC system costs. So we'll send you this study as well, because I know you're gonna go, well, where'd you get that math? Okay, so stop looking at this. I'm gonna show you this 34,100 number. So I'm gonna give you a couple of case studies, and I'm gonna tell you what I think that they ended up with for savings. So case study number 1. They used the R19 T-stud, R19 with the foam in the middle, 2.5 inch thermal break. They used 5 inches of closed cell spray foam. They got an R35 through the wall assembly itself, and they got ACH, air changes per hour, under 0.08. So this is remarkable. They also won the Department of Energy's #1 sustainable home for 2020. So over the top, crazy, unbelievable quality construction. This builder does this every single house, by the way. They meet numbers like this. So this isn't like it's unattainable or this is a one-off. This builder does it all the time. This is a 3,500 square foot house. Their utility bills are $50 a month on budget. 50, so divide by 11, the yearly budget in order to get your monthly budget. So $50 a month, that's for everything. That's for washer, dryer, dishwasher, water heater, and heating and air conditioning. So it's a family of 4, 2 dogs, 3,500 square foot house. Okay, so that's number 1. Oh, here, 3,500 square foot house. 34,000, if the National Home Builders Association is correct, 34,100 BTUs per square foot. That means you're required to use 119 million BTUs to heat and cool that house if it was built between 2000 and 2009. I'm going to assume that the numbers are still about the same at the end of the day because the house got bigger today than what we built in 2000. So if they built the structure 50% more energy efficient, they saved 59 million BTUs. That's a number. That's a big number, right? So here's case study number 2. This is an all-electric house. R19 T-stud again, 2.5-inch thermal break, 3 inches of closed cell spray foam, and 2 inches of dense packed cellulose. They got an average R value through the wall of over 28. Air changes per hour 0.21. This is the very first time that this builder built a house to this caliber that he actually tried to get air changes per hour down this far, and he knocked it out of the park. Utility bills, it's all electric house, don't forget, $100 a month. So they're like $1,100 for the year for everything. The washer, dryer, water softener, water heater, all of it. 2,500 square foot house, family of 4, 2 dogs. I don't know why nobody ever talks about how many cats that they have, but nobody ever brings that up. 2,500 square foot house, 34,100 BTUs, 85 million is what the National Home Builders Association says that an average house in America uses where they're built in, 2000 to 2009. They require this number of BTUs. Save 50% of it, you save 42 million BTUs. You wanna reduce the demand on the grid? You start building to this caliber. So this isn't difficult. This is a complete no-brainer to pull off. So that's case number 1 and 2. Case number 3, 5.5-inch bare naked T-stud, 1.5 inch thermal break. I know, again, they use 5 inches of spray foam. Not everybody uses spray foam. Wait till you see number 4. An R35 through the wall, ACH under 0.25. So this right here, that's a given. This is a given, and the thermal break is a given. Those three things. I'm going to finish with a slide at the end. This is a 1,200 square foot house, so they're small. Used to have a 2-story entryway. Everybody wants the 2-story entryway finished in floor space, so now they're up to 1,600 square feet. Utility bills, $25 a month. That's it, 25. That's for everything. 1,200 square feet, family of 2 plus 2 dogs. So the 1,200 square feet times 34,100. So on average, they're supposed to be using 40 million BTUs to heat and cool this structure. 50% reduction. I know it's over 50. They're probably 80% reduction. 20 million BTUs, that's their savings. That's how you quantify the math of what you're doing, right? So you just keep on building an arsenal of case studies. So number 4, this actually is not a T-stud house, okay? I just happen to like these people because they do it every year, every house, 26 houses a year. They're all sold out through 2022. Unbelievable. It's a gentleman and his niece that run this company. Just super people. They build a double wall. Yep, a wall on the outside, and they come in 1 foot, and they got another one. A 3-inch thermal break through the middle, and they have an R40 through that wall assembly, an R40. Now, R40, that's a big number, but it's attainable, right? There's no spray foam in this, and every single time he gets air changes per hour below 0.25. So let's say that you get your house built and it's to this caliber. I got to get my straw out here again. And you're going to go hang pictures in, and right behind your sheetrock is where they have your vapor barrier. When you go poke a hole through that wall and you're going to go hang your picture, if you don't caulk that thing in or make sure that there's mud or putty or caulk or something around your screw, all the air is going to go out that hole. There are buildings built that have 1 hole, and all the water goes out that hole, and that's where all the rot starts. That's what this is, right? That's what that is. It's like if you're in the north and you put a piece of poly over the top of your hot tub when it's cold out, and you pluck a hole through the middle of it, it spews out of there like Old Faithful. All the moisture comes spewing out. That's what happens in your wall. Okay, that's my straw. Okay, so double wall, utility bills, $25 a month. They do this every month, 26 houses a year. This is what they hit. 1,900 square feet, family of 3, 2 dogs, 80%, they got solar panels up on this roof. So like literally 9 months of the year, they're completely on solar. They just got to give it a little bit of juice in the wintertime and a little juice in the summertime when it's too hot. Here's the proof in the pudding. 15,000 BTU mini split in a 1,900 square foot house. So they meet this, and he does it every time, and they put in this 15,000 BTU mini split. That 1,900 square foot house is required to have 90,000 BTUs. That's what if you do the easy method of calculating how many BTUs you got to have for your size of your house, it's like 90 or 80 or 75. But because they do this all the time, they can get by with this, and that's how they got down to that. So this is This is where how you calculate your return on investment. If you're going to put some money into the wall, so why do we talk about the wall? That's because every window is in the wall. I know, in case you got skylights, but your electrical outlets are there. Every obstruction is there. Every jog in the wall. So all of your, or 80% of all your obstructions or protrusions or something happens on in the wall. So if you can solve for the wall and the rim, it's pretty easy then to solve for the lid and your concrete floor if you have one. Okay, so solve for the wall, you got the rest met. So 15,000 BTU furnace. The first house, they do those houses in the 3,500 to 6,000 square foot range, and like they're like never over 50,000 BTUs for all of that. They got rid of the metal ductwork in these, no more metal ductwork, and they went to plastic pipe. The bedrooms have a little 2-inch or 1.5 inch plastic pipe to them and no return air. So they cut the door off short, and their little bit of return air that they have goes under the door. Super energy efficient, super comfortable houses. Everybody's happy. They save 48 million BTUs a year. That's at 75%, and I bet that they're closer to 80. So all of that, this is just a simple little recipe, okay? So do the recipe. This doesn't mean you gotta do T-studs, okay? So, but I call it the T-stud recipe. You get 1.5 inch to 3¼ inch thermal break through the wall. Why is that? Because that's the worst case scenario. You get that thermal break through the wall, you stop the heat and the cold from transferring through the wall, and you minimize it. And if you do it in the wall cavity itself, there's no maintenance required. Everything goes to sleep, snug as a bug, kind of like being in a sleeping bag. Okay, if you get an R30 to an R40, pretty much through the wall itself. And here's the big one. If you get these air changes per hour below 0.5, that's where, so if you can do this, you're in that 50 to 80% range. And here's my subject too, right? I don't know how many times you open and close the door. I don't know if you have if your whole family's not 9 kids, they got all their friends coming over. So every time you open and close the door, you're letting air out, you're letting air back in. An air-to-air exchanger works where it's like a Venturi vent. So you take your indoor air this way and outdoor air this way and bring it in, and you only have a 10% loss of heating and cooling that happens in the middle because one preheats or pre-cools the other as they transfer back and forth. That's an air-to-air exchanger. So you're just you're making energy efficient structures. So we have hundreds of these that are just like this, and that's our recipe. So meet the recipe. It's a piece of cake to do, and you get this energy efficiency, and you save that many million BTUs every single time. So I'm Brian Iverson. We're here to help you. We're here to help meet the energy codes, and however we can help you out, find us, tstud.com, info@tstud.com. Send us an email. We'll send you all this propaganda. Feel free to forward it off. There's our phone number. No, it's not my phone number. Inside sales guy has that. Okay, I'm Brian Iverson. Thanks for having fun with me today. Thank you.